let's start and say we're welcome to this is the third and planned final lecture on the theory of Lattice-Boltzmann method in this CFD course. So very short reminder, last Monday we started talking about the moments of the distribution function, where we thought that first moments here are, so zero moments are the mass, first moments are the momentum, and then there are in particular second moments that are related to binary collisions. So there is a reason, and we'll discuss this, why these are second moments. And then there are moments beyond this, which in the Lattice-Boltzmann world we often call ghost moments, because they do not directly participate to the solution of the Navier-Stokes equation, which is a little bit untrue, because the third moment is still important, say, yeah. It's not completely unimportant, but the others are, so the higher the order, they actually participate less in the direct solution of the Navier-Stokes equation, even though if we think a little bit harder on them, they are still very important, that they actually exist, and we'll see why. Okay, so we ended on these two problems that, we said we take moments because we'll want to attach different relaxation rates to the different moments, and we don't necessarily know what rates would we take. And the other thing is that this splitting up in moments is in a sense arbitrary. So if we have a rotated coordinate system, we would end up with different moments. And also this definition of moments, because it's an integral over velocity, it is linked to a particular frame of reference. So in a different frame of reference, you get different moments. And the problem with this is that that if you have different moments to relax, yeah, so then that moments that you want to uncouple, and this is the idea, you want to uncouple moments, yeah, if you uncouple these moments in one frame of reference, in a different frame of reference, you coupled them. So therefore, this is kind of a little bit arbitrary, and is not, as we say, Galilean invariant, so it is not independent of the frame of reference in which we state it. Okay, then looking at this in more detail, so comes now the closer look at moments. Let me see whether I can improve here my arrangements. And how moments are actually really defined. So the moments can be identified or defined as a coefficient expansion. The coefficients of a series expansion of the Fourier or Laplace transform. Doesn't really matter whether you take the one or the other. It's more style question. Of the Fourier or Laplace transformed distribution. So as you said, Germans like mathematics. in Abitur you don't learn what a Fourier or Laplace transform is. I hope that you have some idea what this is. So you go you go in the frequency space. Yeah, you take an integral. Actually, this is another important step in going from a particle description to a continuous description, because bless you, if you are familiar with the properties of Fourier or Laplace transformation, then you may know that if you have a Fourier transform of a discontinuous function, like delta functions, yeah, then you get a continuous, then the Laplace transform is, or the Fourier transform of these is continuous. Yeah, so you turn a discrete function, by Fourier transform, you turn a discrete function into a continuous function. And if you think about the fact that, we have particles actually flying around, and these have velocities or momenta at particular points, yeah, then even if we forget about the distribution function, if we take the actual particles and we take a Fourier transform of their velocities, we already get a continuous function. So having a continuous function is insofar important because we need continuity in order to have a series expansion. So series expansion, Taylor expansion. Basically, this is what it is. Yeah. So you have some function and you describe this in form of a series. So and these coefficients. So again, M, A, B, C, and I've written C with this Glyphen. So these can now be written as the derivatives of this in the three different frequencies. So this Xi x is the frequency, so the inverse, so to speak, variable to the x velocity. Yeah. The same thing for the y velocity, and these are the derivatives. So the 8th derivative in x, the b derivative in y velocity, and the c derivative in the z velocity, onto the Fourier transform of f, and this evaluated at xi equal to 0. So the Fourier transform of f I will now write as capital F. And this here is, technically it's a velocity frequency. So it's the Fourier or Laplace transform of the velocity. Crazy? So yes, Fourier transform f. So as we write f is, I should write this up here. Fourier transform. So this is because we're in three-dimensional space, this is a three-dimensional velocity space, this is a triple integral that goes from infinity, from minus infinity to infinity. So we are integrating over the entire velocity space. Then we have f with the microscopic, so this is the non-discretized microscopic velocity, which I write as xi, small xi. Yeah, I write the discretized often with c. Yeah, so but this is the non-discretized version. Into E, so Euler, with the exponent I, so this is the imaginary unit, with the frequency variable times the velocity variable, and we integrate this over xi. So, and now if you are very, very carefully watching, you will notice that the Fourier transform is usually defined e by the power of minus xi. Yeah. So this is, we just turn this somehow around. This is something I never really figured this out. Why we do it? Maybe because otherwise we would have to invert all the velocities. Yeah, is simply the definition of the Fourier transform in this context has the opposite sign than the usual Fourier transform, which actually is the inverse Fourier transform. Yeah, so in the textbook there would be a minus up here, but don't worry about this. Yeah, there is a different sign. That's just a different sign convention. So this is the Fourier transform. Now, if you plug in for the f a sum over delta functions, yeah, then you know if you have an integral over a delta function, it will give you the value of this function at this particular place. And this translates then that you can compute the, so if you plug this in and do all the calculations, what comes out is that the that this simplifies. So this same definition simplifies into this here. So the actual definition, this here up here is the actual definition, and this down here is the simplification for discrete. Discrete distributions. Okay, so in the papers you often read, this is the definition. No, it's not the definition, it's the simplification thereof. We'll need this in a moment. Okay, so these moments, they contain all the information, so there is no better way actually to store things than this, because all the information is inside already, but they are not optimal for calculation. They store all the information for the distribution. The problem is they are not independent of each other. So, for example, okay, we try to understand this by looking at two particles. What are they doing? So, two particles, we can always do a transformation into the centered frame of reference of two particles, yeah, when we describe their collision. So, for example, this particle here would have the velocity minus c, and this particle here would have the velocity c. but there are only two of them. So when you compute the moments, then you get M0, 0, 0 is 2, and M0, 1, 0 is 0 because they have both the same velocity. You will also see that this here is 0 and this here, M0 for 0. This here, wait, this is 2c square. I forgot the c square, yeah? This M0 for 0 will turn out to be 2c cube. So there are infinitely many moments. What you will find is that all even order moments of this are 0, and many, not all, many what did I say? All the odd order moments are 0, and many even order moments are related to the velocity of these particles. So they are basically not, so wait, what did I do? This was, I kind of forgot the moment, okay, this, I mistook them, yes. So this I wanted to say, sorry, yeah? So the second moment is related to c square, and then the fourth moment. So they are not independent of each other. Now, what does a collision change in terms of moment? Because we want to describe our collision in the moment space. So say you have particles coming in like this, and what they will then do, they, for example, go out like this. Yeah? And the way we describe this is, we say, so these are the moments before collision that we write with M, and these are the ones after collision that we write with a star, yeah, just to distinguish them. And inside the equation, we call this here a loss because this configuration, when we have a collision, this is destroyed. So we have to subtract this configuration from our distribution somehow. And the after collision is created, if you will. Yeah? So one is destroyed and one is created. So the one that is destroyed is lost because we have to subtract this from our population, and the one that we generated, we have to add this. One. So this here changes all sorts of moments, not all of them, but infinitely many. Starting from M02, and also because it's turning another place, it would be M200. So if we are in the XY plane. Yes, so this starts at the second moment because there are two particles colliding. This is actually a pattern. Yeah? So two particles change from second order moment upwards. They don't change first order moments and not change zero order moments. So can we recognize this pattern? Look at many, okay, by many I just mean now 3, many body interactions. So, and now you have to remember that I told you that Boltzmann assumed there are only binary collisions. Yeah? So what our theory has already lost this kind of detail. Now let's for a moment think what happens if we had three body collisions. So say we have particles coming in like this in velocities, or okay, say this is now their velocity. Okay, in order to not to confuse this, say this is xx and this is xy. Yeah, so this is now points in velocity space. Okay, I should have the coordinate system in the center, but put the coordinate system in the center. And they, after collision, will, okay, say they have 120 degrees, or to be precise, yeah? Also the other one, because they make up 360. So, and say this is before, this is after collision. You see, this is a plausible collision because it does not change the momentum, yeah, if they have 120 degrees. Yeah, so they have zero momentum in both configurations. And the other thing is this M20, so is equal to M20 afterwards. They also don't change the second moment, this type of collision. Yeah, so if you compute the second moment of this, it's non-zero, yeah, but it has, because we have this 120 degrees, it has the same amount of momentum in the one direction as in the other, and also the same energy. And this is also true for the other direction. And this still happens in this two-dimensional. Okay, now I've written only two indices because it's in this flat space. So, meaning if there is this third order collision, yeah? I mean, if now you would immediately think about, so what is this collision is not, if there is something that's not 120 degrees, then you could take out the part that is not 120 degrees and describe this as a binary collision. So you could subtract this binary collision, yeah, and then you have a binary collision plus this third order collision, yeah. But you see, there's a collision with three particles that does not change the zero, first, and third order moments. But it will change whatever comes afterwards. So we have the three particle interaction, and they change make changes from the third moments upwards. So actually you can extend this. You can have interaction. So if you have binary interactions, what happens? So you have an order of affected moments. You always have to distinguish between even and odd ones, so this will affect the second, fourth, sixth, 8, 10, and so on moments. So if we have a 3-particle interaction, you'll have third, fifth, seventh, and ninth. If we have 4-body interactions, we get 4, 6, 8, 10, and so on. Like 5, 7, 9. Okay, so different interactions do things to different moments. So we could say that the higher moments accumulate the effect of all interactions between multiple particles. Up to a number equal to their order. Now, I have a question. Laplace has a question. Since Boltmann was so successful with describing everything only with binary collisions, are there actually multi-particle collisions in the first place? Yeah? I mean, do we need to think about this? Are there many body interactions in the first place? Because the theory actually says there are none. So what do you think? Are multi-particle interactions somehow important for what happens in the universe? See, you can think about these things in the following way. You have a particle here that comes here and collides with a particle here. Yeah? So we say these two are uncorrelated. So this is Boltzmann's idea. But then this guy will go on and collide with something here. This guy will also go on and collide with something there. Now this will collide with this guy, and this guy, maybe it's not very convincingly drawn, will go on and collide with this guy. So the connection of, they are not, nowhere do all three of them collide at the same time, but these particles here are exchanging. So this particle here is not independent of that particle there because it has exchanged, or that particle here is not independent of that particle here because they have a common interchange in between. Now you could think about it in the following way, that what Boltmann, so that the Boltmann assumption that particles forget about their history and don't have this multi-particle interaction does not mean that they never again exchange information, because what that would mean is that a particle would never, that collides with one particle, would never get its information back. It would basically vanish in a different universe. And this is of course not true. So what actually happens if that after some time, the particle kind of interacts with a particle that has interacted with a particle that has interacted with it already, such that they are still coupled. So in that sense. So there are these high order interactions that need to be there, otherwise the universe would not work. So it would always mean that one particle interacts with the entire other rest of the universe only once and then disappears. This is not what is happening. They are actually here.
So it means that like these, the particles, maybe not interact with other particle that they already have interaction, but some other that have interaction with this other particle, right?
Yes.
Okay.
So they somehow get the information back.
Okay.
So because you get sequentially collisions that drive some interactions. So obviously this is kind of less common than the binaries. And therefore they work on a different time scale. So now these different interactions, we have the next question is how are we going to separate them? I try to give a little bit an intuitive, okay, we love equations, but I try to give an, what on earth? Intuitive explanation. So we take alternative moments with this intuitive concept. So we compute the hierarchy of these moments, knowing that a third order that a three-particle interaction only works from third moment upwards, fourth order from four particles from fourth order upwards. Then for each moment computes and sum, we say this is what we call cumulate. The contributions of all lower moments. Yeah, here again we have seen that high moments depend also on lower kind of collisions. Yeah? So what we are going to do is now we collect all of them from the fewer particle interactions. And then when we collected them, then we subtract them from these moments. So we subtract these cumulative contributions. Cumulative. From the moments in order to have something that only now depends on really third order collisions. Yeah? So, and then these things are supposedly independent. So this is the idea. How we do it comes in a minute. This is just now the intuitive idea. We get new independent moments that do not no longer depend on different types of interactions, and we call these things then cumulants. Okay, how to get there? So, cumulant methods is ever heard about cumulants? No. Is there no? You are doing Krieger, right? No.
Only heard about like commutative property distribution or something like that.
Okay. No cumulants. Okay, so cumulants are very interesting and have applications beyond this, but since you want me to finish, maybe we'll not cover all of this. So our hypothesis for deriving our method is that I've now said this a few times already, quantities that decay on different time scales. So again, we use this relaxation time, and we want to use different relaxation times on different quantities. And in order for this to be plausible, these things have to be independent of each other. Yeah. So you can see if a sixth order moment actually is the mix of second order collisions, third order collisions, and so on, we cannot simply say, so this decays with that particular rate, because it includes things that are happen on different time scales, and we plug all of them together and try to say now they would decay on one common time scale. Yeah. So in order for this to be possible, we have to separate the information that we can say. So these are independent events. They behave on different time scales. Yeah. So we have to make these things independent. That in different time scales must be, so they must be independent events. This means they must be statistically independent. So they need to be uncorrelated. It's not just one can follow the other and then they behave on a different time scale. No, that's not possible. So, going back to our definition of moments, yeah, I write them down again. Moments, so we have this MABC. You remember we take this derivatives. So in Z, and we count up. So these are the H derivative, the B derivative, and so on our Fourier transformed distribution, and we take this at velocity 0. Yeah. So and frequency 0. And now these things are as I already said, these are the coefficients of a series expansion. Actually, so it's not really the coefficients of the Taylor expansion because there's a factor missing. But you can write this F as a series. So because these are the coefficients, we can write this in the inverse way, yeah, as the series. So we can write F as the series over A, B, and C, starting from 0, going to infinity. We have to add here we have to build a polynomial in these variables capital C, which are the frequency velocity. Yeah, so we take this to the power of A and B and C, and so there is one factor here missing from the Taylor expansion. This is A factorial, B factorial, C factorial. Otherwise, it would be exactly the same, and we multiply this with A, B, C. So, because you all know Taylor expansion, right? So you take a function, take their increasing derivative, and you plug this increasing derivative into at a development point, which in this case is development point 0, yeah, and then you can write the function that you took the you can write this function as this series, yeah. So basically, this is what we did here. So this is now the Taylor expansion of F, where you see that the coefficients of this are the moments. So now this here is the original definition, and now we turned the definition around by saying, okay, we have F as a series in the moments. So this here is not an independent definition, because coefficients in a polynomial, they are not orthogonal to each other. Yeah. So if we are looking for independent variables, so what actually makes, say, we still have the same distribution or Fourier transform distribution f. And now we want to state this f, which has a lot of different information in it, as the joint probability function of the different variables that we are looking for. Yeah? So all the information inside this should be a combination of independent variables. Yeah? So now we have not defined these independent variables now, yet, but we want them to be independent. So if you have a joint probability distribution of, say, you have two dice, yeah? So what property do they have? What makes them independent? So if the outcome of one random event and the other are independent of each other, and you join these random events, then you have the product of the probabilities. And the same thing is true for their distribution function. Yeah? So if two aspects, where we now not very accurately define what an aspect is, but something that we can measure. Yeah? If this thing that we can measure is independent of the other thing that we can measure, then their probability distribution, their joint probability distribution, that one is this and the other one is that, would be the product of their individual probability distribution functions. So, and now we can write this down here like this. So we say this should be a product of something of individual distribution functions that I call fi, that only each one depends on one random variable. And this is, say, for infinitely many, right? So we so we build in independence by saying that we can write f as a product of distribution distribution functions, yeah, and because the factorization, so that you can write joint probabilities as a product of two probabilities. This is the definition of independence. Yeah? So we basically ask the question, what are the variables that are independent? By using the definition of independence to identify these variables. Okay? So now we have this product here, and we see that this does not correspond with the normal definition of the moments, because the moments here have a sum, right? So what can we do in order to match these two things together? Using this equation. So, well, what we can do is we can take the logarithm of f. You can take the logarithm of f, and this logarithm of f will turn this product into a sum, where we have the logarithm of fi. Okay? So then we can identify that if we take the logarithm of the Fourier transform of the distribution function, then this sum of the logarithm of this then it can be written as the sum of the logarithms of the individual distribution functions that are independent of each other. And now you can just match these two things here together. Yeah? So you say here we have, so this sum is simply this sum here, and then if we define new variables that are a series expansion not of f but of the logarithm of f, then these variables fulfill by their definition the property of mutual independence of each other. Yeah, so this is the idea behind this derivation. So we get what we now call a cumulant generating function. So where we have the logarithm of f is here this big sum from 0 to infinity on xi xa xi y by the power of b and xi z by the power of c, and okay, we have some coefficients that are not really essential, and this into what we call now CAB and small c. So, and this then again can be just translated in the same way as we had this before, that say CABC is then the derivative of xi x a xi derivative xi y, so the beat derivative, I don't know how to say this properly, and set the c derivative. Now the difference just is that this is the logarithm of the Fourier transform, and still this is evaluated at 0. So these things are called cumulants. So they are independent moments. And now they are allowed to have different relaxation rates because they have, by definition, they are related to, they encode unrelated events. Yeah? So everything that was happening to binary collisions is already deleted from all third-order cumulants. So when we now observe what cumulants are, and usually most people that come to me hearing about cumulants hear about cumulants the first time. So let's see what we observe, what cumulants are. Cumulants are observed to be intensive quantities. The students always have to ask what is extensive and intensive, but you're familiar, right? Or not? So, okay, an intensive quantity, like intensive quantities are the ones that do not add up. Yeah? This is like velocity and temperature are intensive quantities. Velocity and temperature. So moments are extensive quantities. These are the things that add up. So, mass, momentum, and energy. So, okay, small comparison. Moments. So what do we have in moments? So we have, for example, we have momentum, mu, so this would be one moment. And then we have energy. So, and the energy is, the energy that you find in the moment is a thermal and the kinetic energy combined. So there is a thermal energy that's related to the speed of sound squared times the mass of the particles divided by 2, plus there's a kinetic part, so this is the scalar product of the velocity of the macroscopic velocity with itself multiplied by m half. So one thing that you already recognize is that momentum and energy is not independent of each other, because there is a part that is related to the momentum is inside the energy. Yeah? Now compare this to cumulants. So in cumulants, you'll get the velocity without any relation to the mass. And that's very interesting, you get the temperature. As like 3cs square half, and this can be translated to, the Boltmann constant is just a translation variable that translates, that combines, that turns energy into temperature, right? Or scaled temperature, or the moment, or the cumulant actually. You see, this is extremely funny, because apparently cumulants are very, very abstract concepts. So, but when you go through the mass and you see what actually pops out is the stuff that intuitively we all know much longer than the other stuff. Yeah? So I would say that mankind, and maybe also you in particular, when you were little, you had a better idea of something has a particular velocity and something has a particular temperature than saying that something has a particular momentum and a particular energy. So these things here are things that you actually feel and observe. These are the cumulants. Yeah? So in that sense, they are pretty simple. Actually. Okay, so it's already 9 o'clock, so I take you a little bit longer. But then we finish on this subject today. So say
I think she already sent an email that we have lecture and we will gonna do later, so it's okay.
Yes, I think your boss should also appreciate that you learn here important stuff. Yeah, I mean, so also I mean now okay, since maybe if you're not doing Lattice Boltmann for the rest of your life, but even if you do some sort of correlation stuff or machine learning stuff, using cumulants is very interesting, because cumulants are the things that really separate information according to their source. Yeah, so this has beyond Lattice Boltmann a lot of different applications. Yeah, so we don't go into this in this lecture here, even though we only have a few more minutes left. But these things obviously have many applications also in different different ways.
Currently we are doing machine learning stuff.
Yeah.
So that's very good.
Yes. So say the equilibrium that we usually have is kind of a Gaussian thing that has an average velocity, and it has a variance. The variance is related to the speed of sound square, so the standard deviation is related to the speed of sound. Yeah. So this is the Gaussian. Have you seen Gauss standing outside there on this hill?
I saw him on the outside of Schloss Arcade.
Aha.
Gauss,
Okay.
Friedrich Gauss.
Yes.
Very famous guy from Braunschweig.
Yes.
With formula something like n over n plus 1.
Okay, yeah, that one. This is one that he did as a small child. Yes. So, you know, the granddaughter of Gauss used to clean the house of my mother. So yes.
Is there still some of like relevance?
No. Yeah. So no. The actually the Gaussians they left this area and they were moving around. So most of them live somewhere else now. Yeah. No, they are not. They are no longer in Germany. They went to. Some of them went west and some of them went east. Apparently.
But
yeah.
he spent most of the time in Göttingen.
Yes. Yeah.
Maybe someone there.
Okay, let's look at the moments and the cumulants of this equilibrium that we call M00 now equilibrium is equal to rho. So for the zero order cumulant, it's a little bit confusing. We don't really, there's not really a good definition of this. It would actually be something like the logarithm of the density, but I put this in brackets because this could get. Actually, the zero order cumulant is something that's not used, and we don't really care about this because this is a conserved mass is a conserved quantity, so we just forget about this. Yeah. The first order moment of the equilibrium is here this momentum. The first order cumulant is just the velocity. Then there are several second order moments. We don't go through all of them, but here we'll have cs square, speed of sound square, plus ux square times rho. So basically this gives you Cs squared times rho is the thermal energy, and ux squared times rho is the kinetic energy. And this, the cumulant of C200 equilibrium is just Cs square. Cs squared, the speed of sound, is also related to the pressure, but more strongly to the, more directly to the temperature. M110 equilibrium, so this strange guy would be ux times uy times rho. C110 equilibrium, this is 0. M11, so I take out one specific one here. This is ux uy, so this is first order. This goes into Cs squared plus u z squared times rho, and this, as with all other cumulants that come from here, they will all be 0. All cumulants above the second order cumulants in equilibrium are 0. The Gaussian distribution has only 2 non-zero cumulants. So, why does this thing here look like this? What this actually is, and now you can relate to this where we talked about independence. Yeah. So what the Gaussian distribution actually encodes is that the variables here are independent of each other, and independence means the thing factorize, and this is the same thing. This is basically the same thing here, because the moments of the Gaussian distribution, so this moment M112, yeah, this is actually can be written like this. So it's the equilibrium of M110 times the equilibrium of M002, and then we have to normalize this by rho. By the way, you could also say, by the same token, that this is the equilibrium of M100 times the equilibrium of M010 times M002 equilibrium. So this is the same thing. Then you just have to divide by rho square. Now, there is, when you write these things down in moments and in cumulants, there is a small but important difference if you translate this thing here into moments. So you can write cumulants in moments, and you can say that if this moment here, if this cumulant here is 0, what does it mean for moments? So if we write down the equilibrium moment that we got from cumulants, which I write here with a C here, yeah? So we take this C001 equal to 0, yeah, and translate this into moments and write this as moments. So what comes out then, and we put it to 0, and what comes out is that we get M110 times M002 divided by rho. And now you can say this is apparently the same, but there is one important difference between these two things here, because this here is M110 in equilibrium, so these things here in equilibrium, and this, if you write it in cumulants, it turns out that it is the moment in general, not necessarily implying that they are in equilibrium. Yeah, and this makes, so in the modeling, this makes a difference. Yeah, because if you write now your collision operator in terms of moments, and you ask what is the equilibrium of that particular moment, then you would say, okay, the equilibrium of that particular moment M112 is the equilibrium of the moment M110 times the equilibrium of the moment M002, because this is what moments imply. When you derive the same thing from the perspective of cumulants, then you would say the equilibrium of M112 is equal to M110 times M002. Yeah? Just always. Not when they are in equilibrium, but also when they are not in equilibrium. Okay? So, and that makes a difference, obviously, when they are not in equilibrium, which they could be. And so this is maybe also the last thing that we try to understand today. So the same, so when we are in equilibrium, obviously this is the same, yeah? So these two things, globally speaking, they have the same equilibrium. The problem is, how do we compute the equilibrium of one moment when the other moment is not in equilibrium? That's the point, yeah? So, because now, okay, I should potentially explain. So, if you do lattice Boltmann, yeah, then there would be something. Then you will come along these multiple relaxation time methods. That does exactly what we have been talking about. So we split things into moments. We identify their equilibrium function, and then we relax these moments in different ways with different rates. And now we do the same thing. We just derive our equilibrium from cumulants, and then we identify that cumulants give us a different equilibrium. So the equilibrium of this particular moment we were talking about, this M112, does not just depend on the equilibrium, but it also depends on the non-equilibrium of the other moments. Yeah, so this is something that physicists just can't really agree. Yeah, so equilibrium cannot depend on non-equilibrium. That's not possible. Still, the equilibrium is the same, just the way to the equilibrium. Yeah? So where do I go to with my moment M112 if the moment M110 is not in equilibrium? That's the point. So last thing for today, so we have this M112, and you see this M110 equilibrium times M002 equilibrium. So suppose we are in a coordinate in a frame of reference where the velocity is 0. Yeah, so for example, where ux or uy or both of them are 0, right? So this will turn this into 0. No matter whether M110 is not in equilibrium or not. One thing I should say is that M002 is never 0. Because, you see, if we look at this, okay, so this would be similar to this one, yeah? Even velocity is 0, then you still have cs squared times rho. So this is never 0. So, okay, let me try to explain what is happening here. I'm talking about this particular moment because of the observation that when you do this with moments and you relax this thing to its equilibrium, which is 0, then you get a very strange behavior, which for a very long time we could not explain. So simply the code does not work properly. And the explanation for this is, it turns out that this M110, as you remember, that this is related to the binary collisions. So this thing usually is not in equilibrium. Yeah, and we control this by setting the relaxation rate to a particular value that, okay, so it's not, it's difficult to get independent of this M112. So you want to put this M112, you would have to have a different time scale for this in order to make the method stable, yeah, because roughly speaking, so these first order collisions, they should happen much less often than the second order collisions. But you get into trouble whenever you put this to a different value. And I now try to explain this. So let me draw 3 pictures here, which should indicate the distribution of momentum. I'm going to explain what I mean with this. So say we have so we have our velocity space with the velocities in x direction and in y direction. So okay, I apparently wrote x upwards, and so xc1, xc2, yeah. And actually we are in 3 dimensions, which I cannot draw. This is the reason why I draw 3 of these plots, yeah, where this plot here is the one for xc3 is equal to say minus cs, yeah. So in negative direction. So you see, we have a 3-dimensional plot, and we just get three cuts of this. So here, that would be in the center, and this here would be in positive. Yeah. So we have our population, our population in this frame, and we cut through 3 frames. And now, suppose there is suppose this moment M110 is non-zero. So it is itself, it's not in equilibrium. Or going a little bit back, if we draw contours of a Gaussian distribution in this frame, yeah, we would get a sphere, obviously, yeah. So, but if M11 is not in equilibrium, so it's not 0, then this original sphere would be kind of stretched. So it would look like something like this. So this is so the x, the xc1 and the xc2 direction, they are correlated with each other. This is what a moment M110 actually means. And this is the situation that we have in real flows. Yeah. Excuse me.
It look like ellipsoid?
Yes. Yes, yes, so it is stretched. So the velocity distribution is stretched because on one side of this point, the particles are faster than on the other side of the point, and when they come here, so the part that came from the quicker side, yeah, they will be stretched upward in this direction, and the other one that came from the slower side, they will be stretched in the other direction. So the stretching of this of the population is what gives us the stress in the fluid and defines the diffusion of momentum. So now here would be this ellipsoid, and you see this M110 is the distribution of this stretching inside this Xc1, Xc2 layer. And what you have as the M112 is the distribution of this stretching in the the variance of this like kind of the width of this stretching in the third direction. Yeah? So this M112 is 0, or the equilibrium for M112 is 0 because the equilibrium for M110 is 0. Yeah? Meaning no stretching in the other direction. So if we draw this here, so zero distribution or zero variance of the stretching in the orthogonal direction means that, so if you have zero variance of something which is not zero, then you have it all in one spot. Right? Can you imagine this? So you have something, and this is not distributed. So it must be in one spot. Yeah? So meaning that if you go outside of this spot and you look at the equilibrium, this would be a perfect circle here and a perfect circle there. Because all of it is in the center. Yeah? So this is what would happen. What happens if you assume that M112 goes to its equilibrium, which is 0, while M110 is not in equilibrium. Yeah? So, and now you see why this makes us trouble in the Lattice-Boltmann method if we implement it like this, because this M110 is not usually in equilibrium, so we get this stretching. But if we put M112 in equilibrium, we put all the stretching in one point and do not distribute it. Yeah? So this happens when you use moments. If you use cumulants, then what happens is that the cumulant distributes the stretching proportional to the amount of particles that it finds on each layer. So it will also stretch. It will also stretch in, I should probably draw this a little bit more like, so it will also stretch here, but so it will be a little bit stretched in this place. Okay, I'm not drawing beautifully, I know. But it will distribute the stretching of the distribution kind of equally over the different velocities in the orthogonal directions. Okay, so this would be like here. This would be the cumulants, and the other one would be if we do this by moments. Okay, I'm not completely sure whether I got everything now across with this very brief explanation. The thing is actually how we got to this idea in the first place, because of course we did all of this with moments before, and everything was fine until somebody tried to simulate an organ pipe with this. And so the entrance of an organ pipe is very narrow in two directions. And back then there was no crit refinement, so this is many years ago. So they could not refine the crit, and they had a very large space, so they had very few points in this entrance. And this particular example did not work out. Yeah, and this was actually the reason why it did not work out is because you confined the flow not only in one direction but in two directions in the same time. Yeah, and within this confinement, this first order moment suddenly played a role that it would not play if you have a two-dimensional setup. And then, we thought about this and say, okay, actually, yeah, this absolutely makes so the way moments behave absolutely makes no sense, because if you relax this first order moment, what you do is you tell the second moment to be squeezed in exactly one point instead of equally distributing that information. Yeah. So by that, what it means, it's not independent of the other direction. And then what we did is we simply said, so okay, the M112 should be, their equilibrium should be M110 times M002. Yeah, but this was completely ad hoc, and then we see, okay, cumulants do this by itself. That's a little bit the history. And now I actually talk to 9:30. Okay, this is now the end of the theory session of this lecture. I will stop the recording.